All right, if you look at number 3, it says we're supposed to evaluate the definite integral by the limit definition. So there's an easy way to do this if we use, just definite integrals. But that's not what they're wanting us to do here. They're kind of wanting us to still bang it out the old hard way with the limit. And it's not everybody's, usually the early ones are the easier ones, but maybe not in this lesson so much. It's not that this is hard. They're asking, if you think about the function y equals 6, because that's what we do is we take this part here and say that's the function. It's just a horizontal line. And they want us to look at it between 4, 1, 2, 3, 4. So between here and 10, which I kind of tried to draw over here. Now you can see that this is just a rectangle, isn't it? So if I know that it's got a height of 6, because from the y-axis to that line is 6, and I know if it goes from 4 to 10, it has a width of 6, I know that the area is going to be 36, so the integral should give me a value of 36. But they want me to actually do this, and if you're looking in your book, let me flip over there to page 274, they're wanting you to use this process of the limit. So here's what we're going to do. We're going to say, okay, it goes from 10 to 4, so my starting value is 4, ending value is 10. If I want to find my change in x, remember what we do is we take the ending value minus the beginning value, and that's going to be 6, and we divide it into n integrals, okay? Because if we're going to do the limit process, we're going to try to have an infinite amount of rectangles and take the limit as the number of rectangles approaches infinity. All right, so how are we going to write this? Okay, here we go. These aren't my favorite either. I really like doing it the short way, just like y'all do. Now my change in x, which they have started writing this now sometimes as the norm. And there was this discussion in the book about the fact that the rectangles don't have to be of equal width. They can be of unequal width, and they gave you some examples, though they're not going to give you any problems to do like that. And so they just say that the norm is the width of the largest rectangle that we might make if we drew a bunch of rectangles here. So when you see that, if you're looking on page 274 and you're looking at their notation, is the change of x approaches 0. And that's the same thing as letting the limit of n go to infinity. Okay, we'll rewrite it that way in a minute. But first we got to write it as the sum. The sum I equal 1 to n. Kind of hard to get these small little letters to show up on the iPad. And then we have our function where we're going to plug in our I value. They write it as c of I is a subscript, times your change in x of I. Okay, so what we're really going to do is we're going to take a limit as the change in x goes to 0. We're basically saying we're getting n rectangles, so we're going to let n go to infinity. And again, they would write it like, okay, so we're still thinking about, these little rectangles. They're each going to have a width, and they're each going to have a height, and the height is the function value. All right. Now, what's kind of nice about this one, at least, is its limit as n approaches infinity. I equal 1 to n. And our function value, no matter what we do, is going to be 6, isn't it? And our change in x, no matter what we do, is going to be 6. So the limit as n approaches infinity, I mean, if you think about these, actually I should write 6 over n, I guess. Because the change in x, which we're still talking about all the little rectangles. So it would be 6 divided by n. We actually figured that out over here to the side. So I equal 1 to n of 6 times 6, and we can pull the 1 over n out front. So that's the limit. N approaches infinity. The sum, I equal 1 to n, but we've got that 1 over n out front. Let me write it in blue since I forgot to put it in there. Maybe it'll be easier to kind of do. 6 times 6. Okay. Which is 36. Could have written 36 there. Now you're like, how are we going to get rid of that 1 over n? Well, here's what happens. Do you remember that if I have 1 over n out front, limit of n approaches infinity, and I have the 1 over n out front, and I actually do this process. This would be I equal 1 to n of 36, but do you remember that when you're summing things and you have a constant, it's 36n. So if I actually, the math does work out. I know I was sitting here for a minute going, what? This doesn't look like it's going to work out, but it does. The limit as n approaches infinity, I equal 1 to n of a constant is 30, or the sum of I, this part, I'm misspeaking here. Just this part of a constant, that sum, we have a formula for that. It says it's 36n. But I got an n out front, so when I actually look at the math here, these n's are going to cancel out, and the limit as n approaches infinity of 36 is just 36. We knew what the answer should be because we know how to find the, let me write the answer up here and circle it because it's not fitting in that little space. We knew what the answer should be, but if we wanted to show it, we had to talk about the function value at each one of those little changes in x. We had all these little changes in x to represent the width of our rectangles, but what was the function value for each one of those? This could be harder. Usually it is harder. This one actually was easy because no matter what rectangle we're looking at, it had a height of 6. The function value was 6, just because this was an easier one. Let's do another one, just because I know for a lot of people, even for me, these can kind of trip me up sometimes. So let's make sure we do enough of them that we've got plenty of stuff on record here. Okay, so we're supposed to do this with the integral process. I think 7's already done, but x cubed dx, I think I've already got a video on 7, so I'm just making one on 1 and 5 here. All right, so I want to say my change in x is going to be my ending value minus my starting value divided into n, or I. If I want to, make this I, I'll make it an I here. That's going to be 2 over I. So my width, if I'm going to write this as a sum, I'm going to take the limit as n approaches infinity, but it's of the sum of I equal 1 to n, because remember, we don't put negative 1 to 1 here. That's given us our, basically our width of our rectangles and what the total width is going to be. But when I take a limit, I always do a sum from 1 to infinity because I'm going to make an infinite amount of rectangles. So it's going to be the function value times the change in the x. But I know what my change in x is. Let me just kind of keep going over here just to try to use my space as best as I can. The limit as n approaches infinity of the sum of I equal 1 to n. My width, let me try to draw a little line here. My width is 2 over I, if I plug it in. And my function value is something cubed. But what am I going to write here? Okay, here's where it gets a little tricky. I'm going to have to come down here to write, as I didn't leave enough space, as usual. My function value is x cubed, okay? So it's going to be something cubed, okay? But it's going to start at negative 1, and then I'm going to add in this 2 over I for each little rectangle. You're adding in the 2 over I. Let me go back and change some things up here. I think I used my I too early. If I'm going to divide it into, let's come back up here and look at this part right here. When I do my change in x, they usually, let me use n just so I'm being consistent with the book. Okay, so this would be 2 over n here. So it's negative 1 plus 2 over n, but remember, I've got, I is just counting off from 1 to infinity, all these little triangles that I'm making skinnier and skinnier. So there should be an I here, and that way I can say, well, I've gone 0 I's, I've gone 1 I, I've gone 2 I, 3 I, 4 I, 5 I, all the way up to infinite amount of I's. But I have to put my starting value here. In this integral, we go from negative 1 to 1. So you have to kind of account for that when you're saying, I'm not going to start at 0, or I'm not going to start at negative 5. I'm actually starting at negative 1. That was this part right here on the integral I have to account for. So I'm going to say limit as n approaches infinity. The sum I equal 1 to n. my function value is negative 1 plus, okay, my width of my rectangle should be negative 2 over n up there. I had to go correct that. I used an I, and I really needed to use the n there. So it's 2 over n, but then I got to count. So I'm going to put an I there. That I is kind of like my counter going through saying I'm on my second rectangle, I'm on my third rectangle, I'm on my fourth rectangle. So I needed to kind of adjust that. And so now I need to put my width of my rectangle is again this 2 over n. I changed it from 2 over I to 2 over n just to be consistent with the notation in the book. Because we can switch letters out, but it gets really confusing. So I'm just trying to be consistent with the book so it's less crazy, okay? All right, now, if I look at this, I can pull that 2 over n out front and then put my sum, because n is a constant. It's going to go to infinity. If you remember what usually happens, a lot of that stuff usually cancels out. So I got 2i over n. Now, this gets kind of confusing, so I'm going to split it up into separate little, I'm going to do limit as n approaches infinity. I've got a lot of simplifying to do. I'm going to leave this 2 over n. Actually, I'm going to take and split up my sum into two separate parts. And I'm actually going to put the 2 of n with each part, because if I don't do it, a lot of times I forget to do it at the end. It's kind of like it needs to be distributed. So it's 2 over n times the sum I equal 1 to n of negative 1. And then, again, this is a whole, I'm going to take the limit of the whole thing. I'm going to make my terms in different colors just so you can see them. And then 2 over n, sum of I equal 1 to n. And I'm going to take this 2i over n here, the second term. All right, I got to do the limit of all those things. Now, I need to simplify this. I could put that negative out front for that 1. That would be a negative 2 over n. And the sum from I equal 1 to n of a constant is just n. So that's going to turn into n. I'm going to take the limit of all this in a minute. And so right now I'm just simplifying the part that's in the bracket. I just kind of stuck that limit out front because I forgot to write it. Now let me go to the second one. I could take another n out. I could take this n right here and move it out front, and that's what I'm going to do. So that's going to become 2 over n squared out front. And then I could take another 2 out front, so that 2 times 2 is going to become 4. I'll just write it like that for now. And then I've got the sum, I equal 1 to n of I. Okay, now this is where I have to go back to, I think it's page 260, and get that formula. I think it's n times n plus 1 over 2. I'm going to check real quick. And it is, okay? It is n times n plus 1 over 2. So now I've got the limit, n approaches infinity of, now this 2, let me go ahead and simplify. This is just going to be 2 over here. I'll go ahead and get rid of those n's on that first term. Then I've got 4 over n squared, and then the sum of I equal 1 to n of I is n times n plus 1 over 2. This is going to be a mess because if I can't copy to the next page and my video is running out of time, so I'm going to try to simplify this as best I can. It's going to get kind of crammed in here though. All right, so the 2 goes into 2 once, 2 goes into 2 4. Oh, it's 2 times on my word. And then I've got an n that cancels out, and it leaves me just an n here. So what I've got now is the limit, n approaches infinity, of 2 plus n plus 1 over n. Okay, now I got to divide that up. I'm not going to recopy the limit just because I should be writing limit n approaches infinity, but I don't have room, so I'll just put, well, let me just kind of just put limit there, okay? So that's 2 plus n, remember I got to split that fraction up, n over n plus 1 over n. As I take the limit, n over n is 1, so I get limit of 2 plus 1 over n. And if I plug infinity into 1 over n, that whole term is going to go to 0. So it's going to be the limit of 2 plus 1, which is 3.